Justin Miller, Code Physics here. Good day to you. And what have we got on the menu? We've got ourselves some more optics, some optical illusions. Ooh, maybe, maybe not. Is it magic? Is it science? You be the judge. Anyways, we're going to look at some refraction today. And refraction is ultimately the tendency of light to bend, they say, change its direction at the interface boundary between two optically transparent materials. So it only deals with light wavelengths that are able to go into the material in question. So we say optically transparent such that light can travel through it. Now that's not to say that sunlight doesn't reflect off of it, but sunlight goes through it. Anyways, something that's optically transparent in the visible realms of wavelengths, glass, right? See right through glass. It's a nice big thick chunk of glass here, and there you go. Got some glass, can see right through it. That's because light goes through it, right? We've got ourselves some laser light. I got a nice little laser here, and if I put this glass in front of it, what happens? Oh my gosh, the laser light goes through it. A little bit of reflection occurs. You may be able to see some little green dots there on the actual glass surface, on the entrance and exit surface. That's where we're getting a little bit of reflection going on. But the majority of the light is transmitted through, and well, it just goes through, just like that. That's what allows us to see through glass, right? Light can travel through it. Well, refraction is a tendency of light to change its directions at the interface boundary between two optically transparent materials. We'll write that down here in a second, but this is what we want to look at, is how that takes place. So here's a little example, not an example, demonstration. How about that? So I'm going to go ahead and hold this glass like this. I'm going to put my eye right there, and maybe, hopefully you can see my eye. I can see the camera, so well, you should be able to see me in principle. Whether it's really small or not, it's a different story. Well, what happens if I put, say, my finger right here? Well, now you see the top of my finger. That's true, and you should be able to see my finger through the glass, but you don't see my eye anymore, right? What happens if I go ahead and I change the orientation of this glass, rotate it, and see what happens? So I put my finger there, and you can still see the top of my finger and the bottom of my finger. Put my eye right there, and then I rotate it. Ooh. But now you can see my eye, but hopefully you notice something else too. You notice that my finger that is coming through the glass isn't in the same place or aligned with my finger above and below. And that has to do with our refraction. So it looks like I've basically changed the location of my finger. Ooh, you see it this way, but that's not what's really going on here. I'm just rotating the glass, and it changes how light interacts with the actual the surface boundaries. So this is what we want to look at. So, a little magic going on. How do they make people disappear? Oh my gosh, I have no idea. Anyways, refraction. Oh, that's already bad news. We're gonna do some blue. The tendency of light to change direction. And often we just say bend. At an interface boundary. Between two optically transparent materials. TWO. Oh my gosh. So what are some optically transparent materials? Air is optically transparent, right? And we're talking about with wavelengths that are in the visible region. No refraction happens with all wavelengths. Depending on what the substance is, we may have refraction or no refraction, just depending. So we're going to deal with our visible light range, but it does happen with things that aren't in the visible spectrum as well. The air, clear plastic, glass, those are some really common things that are optically transparent that we deal with on an everyday basis, right? All right, so there we've got some refraction. So let us take a look at this. Notice I have something I'll set up here. Carefully do this. Lowering this on down. And what I've got here is some materials that has a little magnet on the back so it can stick to this, but it's transparent this way. It's just a piece of plastic. It's like lucite, some high density plastic. Anyways, these, same thing, these are just little triangular shapes. Ooh, that one gets a little bit weird looking at, but anyways, that's what we've got. And I've got a little light ray box that shoots out some lasers, and it's a nice red laser. Let me get this kind of set up here. And we'll see what we can do with this. All right, that looks okay. And let me just have this out on the side to begin with. And I'm gonna dim the lights here and turn this on. So deal with this one moment. Turn the lights all the way off. You'll be able to see me a little bit, but let's just do this. So I plug this laser in, and zoom, you got this nice red light. Shoots out. Ooh, nice straight line laser light. Don't worry about up there. What I want to do is I want to put this plastic, this transparent material in front of it. So what's going to happen? Well, as you probably guessed, it goes through it because it's transparent. We can see the path of it kind of imprinted on this back white side of it. So it goes in, comes out, fantastic. Looks like it just goes in a straight line, right? So in this orientation, it doesn't seem that there is any change in direction of this light ray, right? The interface boundary is here, and there's another interface boundary here. The interface boundary is where we go from one material into the other. So we've got an air plastic interface boundary here, and then we've got a plastic air interface boundary here. So let us do this. I'm going to change the orientation of this and see if we get any noticeable change in direction of the light ray as it goes from air into the plastic. Ready for this? I'm just going to go like this. Oh my gosh, don't worry about this. This is some reflection going on over here. We're always going to get some partial reflection that obeys the law of reflection. What we're interested in is light coming out this way, and then it enters this plastic here. Notice that it's not traveling in the same direction. If I took this plastic piece off right now, that's what direction it would travel in its absence. I put this plastic piece in, and through the plastic, it's going at a much different angle than it's at going through air. So it goes in and it bends, changes its direction, and then it bends again as it goes from the plastic back out into air. Bends that way. And if you look closely, you may be able to notice that this ray here and this ray here, the ones that are out in air, are parallel to one another. The change in direction takes place within the plastic. But notice that there's also an overall lateral shift of the path of the light ray. Even though this and this are parallel, it's been shifted because of transiting through this. So there's how it would be. Now there's how it is. So what we have here is that the change in direction depends on the materials, yes, but it also depends on the orientation of the interface boundary relative to the incoming light ray. So if we have that it travels in a direction that is completely perpendicular to the interface boundary, we don't seem to get any change in direction. It goes in, comes out, same direction it was initially going. But when there is an angle relative to the normal, a non-zero angle, then we do get some amount of change in the direction. And the greater that is, the greater that change is. And there's all sorts of cool things that end up happening. So that's what we want to look at here, is just this change in direction that the light ray makes within the material. That's the refraction. All right, so let us go ahead and do that. I'll show one more little thing. It's kind of cool looking. Myself a little green laser light. I can kind of sweep it across and go whoosh. It goes in, comes out. Now look. That's the direction that it would go. And then it's going in some completely different direction within the glass itself, or within the plastic. We can do it with green, we can do it with red, with whatever. Normal incidence, and then some other angle. And then we get all sorts of reflection going on too, and we'll take a look at that. But this is what we want to look at, a refraction. So, turn some lights back on here really quick. Move this out of the way. And proceed onward. So we may come back and look at some other stuff here. I'll leave that there. But let us just go ahead and start looking at some consequences of this. So you may say, why does refraction happen? What's that all about? And ultimately it has to do with the speed of light. The speed of light depends on what light is traveling through. When light travels through free space, empty space, the vacuum, it travels at its quickest rate, 3 times 10 to the 8th meters per second, 3 significant figures, the speed of light in a vacuum. But when it travels through other materials, it slows down. Now, I don't want to say all of a sudden, instead of going 300 million meters per second, it's going like 10 meters per second. It still goes really fast through the other materials, but substantially slower than its true speed in a vacuum. And what this ultimately ends up producing is a change in its path as that change in speed takes place. So, refraction is due to the dependence of the speed of light and the material through which it travels. TR. Through free space. The speed of light is C is equal to 3.00 times 10 to the 8th meters per second. 300 million meters per second. Pretty darn quick there. So, in other materials, it's really not a material, right? Free space. It's a lack of material. But in other materials, speed of light is less than c. So we don't want to call it c anymore. C is reserved specifically for the speed of light in a vacuum. So we have to have some other speed, and we just call it speed v, the speed of light in a given material. Well, what we do is ultimately define something about a material. Instead of defining specifically the speed that light travels through that given material, we define what is known as the index of refraction of the material, and have that be the ratio of the speed of light in a vacuum to the speed of light in that given material, such that we have some manageable numbers, because we don't want to be having to deal with really huge numbers, 250 million meters per second, and so on. We can kind of compress this down and talk about some numbers that are relatively easy to get at. We define the index of refraction of a material, N, as N is equal to C divided by V, where V is the speed of light and the material in question, for which we're defining the index of refraction. So these two go hand in hand. Ultimately, yeah, we could kind of correlate it just with the speed, but this ends up being really easy to do. Why? Well, for one, since C will always be greater than or equal to V, N is greater than or equal to 1. When is C equal to V? Well, when we're talking about free space. Or if we round something off to some significant figures like air has a speed that's very close, light and air has a speed that's very close to the vacuum speed. It's 3 significant figures, it's the same. So in that case, we'd say that the index of refraction of air is equal to 1. The other materials, not so much. And we just define indices of refraction. Glass, for instance, has indices of refraction that range from 1.2 to 1.7, depending on the composition of the glass, what type of glass. There's all sorts of different types of glass. Flint glass, crown glass, all sorts of things. So got variations, but for a specific material, we can define a specific index of refraction that ultimately gives us the correlation of what the true speed of light is within that material. All right, so what do we do with this? Well, we appreciate, number one, that we get numbers that are relatively small. Generally, the indices of refraction range from 1 to, for visible light, I should say, for visible light, range from like 1 to maybe 3, 3.5. That starts getting really high for an index of refraction. Usually it's in maybe the mid 2s, 2.9. We don't see much over that, except with exotic materials. But usually we're actually having indices of refraction somewhere around like 1.5, 1.7, stuff like that for our everyday glasses and plastics and stuff like that. Water, clear water, pure water has an index of refraction of about 1.33. 1.333 gets ultimately used a lot. And that correlates specifically with the speed of light within water. Anyways, that's what we got. Indices of refraction. So what can we do with this? We now look at Snell's law, which is ultimately the law of refraction, but Mr. Snell got some credit for it because he kind of put some stuff together and ultimately came to some expression that correlates changes in angles and indices of refraction. Snell's law says N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. So what we want to do is understand what this is telling us and how we can utilize it to figure out the direction that light travels through a given material, given enough information. So let's do this. So I'm going to take two materials. We can take material number 1, which has some index of refraction, N1, and then we can take material number 2, which has some index of refraction, N2. And here is an interface boundary between those two materials. What can we do with this? Well, we can take ourselves a ray of light and see what happens with it. So I just go ahead and say, oh, you know what? We've got some light ray that's cruising along, and it comes, and it's going to strike this interface boundary. And it strikes the interface boundary at a particular angle that we're going to measure relative to the normal of the interface boundary. So I'm going to call that theta 1. There we go. We've got theta 1 right there. So we've got the index of refraction of material 1 multiplied by the sine of the angle at which light is striking the interface boundary relative to material number 1. And that's that. So then we go on and say, well, what's going to happen? Well, again, if this is optically transparent material, light's going to enter the second material. That's what we want to be looking at, so let's just go ahead and do that. So I'm going to translate this normal down. So we've got something like that. And now I'm going to go ahead and say, well, this light doesn't keep on going straight because we've got two different materials here with different indices of refraction. So here's something that is possible that the light actually goes like this. Bends, changes its direction substantially. And what do we have here? Well, we've got theta 2, measured with respect to the normal at the interface boundary as well. So that's what this expression ultimately correlates directly with. Indices of refraction of the two materials, N1 and N2, which again trace back to the to the speed of light in those materials, and the angles at which that ray of light is incident and refracted at. So this would be the incident ray. This we could call the refracted ray. And this is just a nice general expression, N1 sine theta 1 equals N2 sine theta 2. Fantastic. So if we know what the indices of refraction are and we know what the entrance angle is, we could go ahead and figure out what the angle of refraction is. Or if we measure both of these angles and we know what the index of refraction of this material is, we can figure out what the index of refraction of this material is, which then would allow us to figure out how fast light's traveling through this material, because once we have the index of refraction, we can always solve this out for V. The wave speed is just going to be the true speed of light in a vacuum divided by N. Pretty cool, huh? All right, so that's what we've got going on with some refraction. And there's some possibilities, some different things that happen, so that's what we want to look at a little bit more as well. So in this particular case, notice that I'm taking this light ray and saying that it is going and it's bending towards this normal here. Well, it's only going to do that for certain combinations of N's, for certain combinations of the indices of a refraction. So what is that? Well, theta 2 we have here is smaller than theta 1. In this particular case here, theta 2 is less than theta 1. And for that particular correlation, it turns out that N2 then must be greater than N1. If you go from a lower index of refraction to a higher index of refraction, the light will bend inward towards the normal. That's just the general rule there. That's what happens. Which ultimately says that the speed of light in this material is higher than the speed of light in this material. V sub 2 is less than V sub 1. The lower the index of refraction, the faster the speed of light. Until you're down to an index of refraction of 1, at which the speed of light is its maximum value, 2 times 10 to the 8th meters per second. So that is the correlation of this. So we can also go over here and do a whole new system here. We take a material number 1 and a material number 2 with different indices of refraction on this side. We can take a ray of light. So we've got some light coming in. But instead of having it bend inward towards the normal, I could say that it actually bends away from the normal. Well, what's going on in this case? We still have ourselves some theta 1 and some theta 2, the incident ray and the refracted ray. We have a material number 1 and a material number 2. But if this is going to be the case, we must have now, well, just by direct inspection, theta 2 is greater than theta 1, which means that N2 is a greater, is less than N1, which means that V2 is a greater than V1. This is just the opposite correlation there we had on the other side. If we bend away from the normal, we are going from a higher index into a lower index, and we'll thus have that the light ray bends away from the normal, which also means that we're going from a lower speed into a material where light has a higher speed. Those are two main things that happen regarding refraction. Now, if it has the same indices of refraction, N1 and N2 are equal, it just keeps on going. no change in direction. So it's only when we have differing indices of refraction. And it is possible to have two different materials that have the same indices of refraction. Possible, not super likely, but yeah, possible. All right, so give me 1 second. I want to erase this stuff up and show you guys some other stuff. And yeah, go from there. So give me 1 moment. All right, so you may look at this and go, oh, that's crazy, bunch of stuff going on here. I got 2 little triangular sheets that are transparent going this way, and you can notice, you can kind of follow this, right? So the light comes out of this, it's traveling along this path in the air, and then it reaches the interface boundary right there. And what happens? Some reflects off, truth, reflects off that way, equal angles about the interface boundary, law of reflection, but some of that enters and undergoes a change in its angle, right? So you can definitely see that. Then what happens? Then it comes out on this side, undergoes a slight change in its angle because the orientation of this boundary is really close to the normal of the surface here, or the path of the light is close to the normal of the interface boundary there. But it goes through nonetheless, and then it comes over here, enters this, undergoes a change in angle, and then it exits over here. So you can notice that here we're going from an index of refraction that is higher in the plastic to something that is lower back out into air. The normal vector here would be something that is like this, right? There's our normal here. So if I went ahead and put another normal like right here across the glass, you should be able to see that this angle here and this angle here are much different. This angle's bigger, right? That angle is bigger because we're going from a higher index to a lower index, and the light bends away from the normal then. Whereas in this case, we have, here's sort of an angle here, and then we've got a smaller angle right there. By some amount, not a huge amount, but by some amount. And this, we have a smaller angle because it bends towards the normal when it goes into a material that has a higher index of refraction. So that kind of gives us both going on there. Smudgies off there. But that's not just it. We've got some other things that can happen here. So I'm going to just take this one out of the way. And again, we notice we get some reflection off of the surface, which is typical, and we get some refraction here, which is just how things are working out. That's great. But watch this. Watch this. I'm going to go like this. Whoa, what just happened? Ooh, see that kind of weird stuff going on? So this is what I want to look at, is this backside right here. So the light enters here, enters right there, sure, undergoes a little change. I want to concentrate on this interface boundary though. Light's traveling through this material along this path right now. And then it emerges out and it bends away from the normal and goes that way. So again, concentrating just on this material, this interface boundary. Well, what happens if I start changing this angle here that it's striking this interface boundary at? Making it bigger and bigger and bigger. Well, this exit angle gets bigger and bigger and bigger as well. But the exit angle is already bigger than the entrance angle relative to the normal right here. So what happens eventually? Well, eventually there's a maximum angle at which this angle of refraction can be. And that will be 90 degrees with respect to the normal right here. This refracted angle is at 90 degrees. Once it exceeds 90 degrees, there's no place for it to go. There is no exit anymore. What happens? We just get reflection. And this is known as total internal reflection. And it's something that you can see when you're submerged in water, in a swimming pool looking up. If you're deep enough, there's usually sort of a little circular section that you can see out of, and then everything else kind of looks grayed out, or really it's a reflection of the bottom of the pool that you're seeing coming back to your eyes because the light can't get out. Anyways, this is what we've got going on. There is a particular entrance angle here, this angle relative to the normal, at which we get a 90-degree refracted ray. It refracts right along the surface. And if we exceed that angle, boom, we get total internal reflection. So what we want to be able to do is define that maximum entrance angle so that we get an angle that is 90 degrees with respect to the refracted ray. And note that that entrance angle can be called what's known as the critical angle. the entrance angle or incident angle that produces a 90-degree refracted path. But it will only happen if we are going from a higher index of refraction into a lower index of refraction. It can't happen the other way around because, well, we need this refracted angle to be larger than the incident angle. Otherwise, it's just not going to happen. All right, so let me turn on some lights again. We can kind of work this on out. See how we get this going on. And yeah, let me just take that off and unplug it. Fantastic. So we define critical angle. Theta sub c as angle of incidence that will produce an angle of refraction equal to 90 degrees. So take something like this. We take ourselves some light ray coming on in. Here is, we're going to call this theta sub c. And what we're going to get is this. Theta 2 is equal to 90 degrees. I can say theta 1 is equal to theta sub c here. 90-degree refracted ray. What happens if we exceed theta sub c? We'll go over here and say here is our normal interface boundary, and we take an angle that's just a little bit bigger than that. That doesn't quite look like the law of refraction there. Reflection. That looks a little bit better. We will have this. Theta 1 greater than theta c. Theta 2 is equal to theta 1. We get no refraction. We get total internal reflection. That's what this is called. So we just get refraction. Refraction. That is it's a boundary, really, or a limit, I should say. A limiting case on angles. For this, though, let's draw this stuff in. We've got an N1 and we've got an N2. N1 must be greater than N2 for theta sub c to be defined. That's it. So that's another possibility that happens. Special case. All right, so that's sort of a nutshell of refraction and some things that can happen. Bend inward, bend outward, critical angle, exceeding the critical angle gives us total internal reflection. Incident angle has exceeded. So we get no refraction, we get total internal reflection. All right, so those one more thing that I just like to talk about a little bit, not get too heavy into, but it's of a general interest, and that is, how do you develop Snell's law? How do you go about that? What physical principles can be utilized to develop Snell's law? Why does light change its path? And what's ultimately utilized to develop Snell's law is what's known as the principle of least action. Maybe a little bit above the level of what we're doing stuff, but the idea is pretty cool in that light tries to minimize the amount of time it's within a given substance. That's how you can kind of look at it. Not like light has some entity, some being that thinks like, oh, I don't want to be in this substance that long. I want to be out in free space. I want to be free. No, it's not quite like that, but it just happens to be that light finds a path that minimizes its time in a substance. So the idea of that is what's utilized. Principle of least action. All right, so here's a little for instance. For instance, I love this. And this is this. Say you're at the beach. You're over here. You're over here on the sand. Here is the water. And over in the water's one of your friends, family member, friend, somebody that you like. It doesn't necessarily have to be somebody that you like, but somebody who's over here. Friend is here. And for whatever reason, you need to get to your friend as quick as possible. Maybe they're in trouble. Ooh, help, help. Something's going on. You got to get there quick. What is the quickest way to get to your friend? Quickest path through space. And you may be inclined to say, well, the straight line is going to be the quickest path. And I'd say, well, that's only if you can move as quickly across the sand as you can through the water, which generally is not the case, right? So let's kind of put some limits on this and say that you're either going to be running across the sand or you're going to be swimming in the water. One or the other. One or the other. You're over here, you're running in the sand. You're over here, you're swimming in the water. Now, I think most people, not everybody, but most people probably can run faster across the sand than they can swim in water. But there's a trade-off, right? I want to get here as quickly as possible. Well, if I run faster in the sand than I swim in the water, going straight there doesn't do it. If I run much, much faster in sand than I do swim in water, the fastest route for me would probably be to run across the sand as much as possible, then swim the least amount possible, right? Or if I swim much, much faster than I run across the sand, let's minimize the time I'm running across the sand and maximize the time that I'm swimming. Usually it's somewhere in between, right? You run pretty fast, you swim pretty fast, but you run a little bit faster. So then what? Well, then you want to be running a little bit more to minimize the time that you spend getting here. So get to your friend. ASAP. Which route do you take? That's the sort of a thought experiment that you utilize to develop Snell's law. So we have some speed that we run in sand, and then some, maybe not quite that steep. Be something like that. We've got some V's of sand, some V's of water. The speed that we run in sand is faster than we swim in the water. There we go. We've got a particular path. What do we have with this? We've got some theta sub s, and then some theta sub w, and depending on, again, what these are, we get some sort of correlation with Snell's law. So we're not developing it here, deriving it, but this is the thought process that's utilized to develop Snell's law. It's pretty cool to think about. Say, wait up, let me calculate this out really quick. How fast do I run on sand? How fast do I swim on water? That's probably not going to be efficient. You just get there as fast as you can, right? You just run probably straight. But truthfully, if you want to get there as quick as possible, there is a particular route that depends on how fast you run in sand, how fast you swim in water. Pretty neat, huh? Thank you, Mr. Snell. Been a pleasure. All right, you guys all take care. We'll come back and do a couple problems here in another installment. Be well.